We will start our problem with a triangle with the sides of 3 and 4. Then, using the bottom side of the triangle as the diameter, we will construct a semicircle which touches the apex of our triangle. Next, from the remaining two sides, we will erect two semicircles as you can see on the sketch. The question is, can you somehow calculate the red shaded area? Now, as I mentioned in the title, this problem is actually solvable in less than 30 seconds if you know what to look for. And I'm going to show you exactly how to do it. Trust me, a lot of people don't know this method or they just don't think in that direction. So I'm going to show you how, and I'm going to prove to you why this method works. But before we get to that, you can pause the video right now if you want to. Try to solve this one out for yourself and then come back and check the solution. Alright, so let's solve this one. So, in order to solve this, you first need to realize that our triangle is actually right-angled triangle, and we can prove this by using an inscribed angle theorem. This theorem states that an inscribed angle inside any circle is 2 times smaller than the central angle that subtends. So, if you take a look at our sketch on the left, you can see that the central angle of our big semicircle is 180 degrees, which means that the inscribed angle at the top must be 2 times smaller, or 90 degrees. So this means that our triangle must be a right-angled triangle. So with this in mind, let's try to solve our red area. You can notice the second fact, that our red area will be equal to the area of the semicircle on the left, which I will label as A1, plus the semicircle on the right, which I will label as A2, plus the area of our triangle, and minus the area of the big semicircle, which I will label as A3. In this way, we can get the area that we want. Now, let's do this in less than 30 seconds. Ready? So, the area A1 plus A2 equals to the area A3, so we can cancel those out. And we will get that our red area equals to the area of the right-angled triangle. The area of the right-angled triangle equals to the half of the product of its legs, so 3 times 4 over 2, which means that our wanted red area equals to 6 squared units. As you can see, this is super fast way, and we're done. But of course, you're probably wondering right now, how do I even know that area A1 and area A2 are equal to the area A3? So this is the thing that I want to show you today and prove to you why this works in any case for the right-angled triangle. So, let's start with the right-angled triangle, and let's label its legs as A and B and the hypotenuse as C. I'm not using any number values because I want to show you that this works in any case. So let's start by erecting squares from each side of our triangle. In this way, we got this image, which I think that all of you are quite familiar with. This image actually represents the proof of the Pythagorean theorem. And we're going to use the same proof, but we're going to use it in a reverse direction. Let me show you. Let's first label the areas of our 3 squares as A1, A2, and A3. And in this way, we know that area A1 equals to A squared, area A2 is B squared, and area A3 is C squared. Now we know that our triangle is right-angled triangle, so the Pythagorean theorem applies. A squared plus B squared must be equal to C squared. And if we substitute the values of A1, A2, and A3, we will get that the combined areas of A1 and A2 must be equal to the area A3. Alright, so clearly this works for the squares. But what if those shapes are not squares? Well, let me show you. Let's say that we have the same right-angled triangle and the Pythagorean theorem applies. But this time, instead of the squares, let's erect an equilateral triangles. And let's label the areas of those triangles as A1, A2, and A3 as before. Now we can say that the area A1 on the triangle on the right is equal to the A squared square root of 3 over 4, which is actually the formula for the area of the equilateral triangle. Now we can use the same formula for the area A2 with the side B this time, and finally the area A3 with the side C. Now let's try to find the sum of the areas A1 and A2. We can substitute the values for A1 and A2, and you can see that we have the common denominator, so we can group this as A squared plus B squared square root of 3 over 4. But remember, A squared plus B squared is actually equal to the C squared, so this equals to C squared square root of 3 over 4. And you probably noticed that this actually equals to the value of the area A3. So, in this way, we have proven that the sum of the areas A1 and A2 are again equal to the area A3. But in our problem, we had semicircles, right? We didn't have triangles or squares. So let's try to do the same thing with semicircles. Let's erect 3 semicircles from all 3 sides of the triangle, and let's start with the area of the semicircle on the right. The area of the semicircle is equal to the 1/2 of the radius squared pi. But notice that in our case the diameter is equal to A, so this means that the radius of this semicircle on the right is equal to A over 2. Now this means that the area is equal to 1/2 of the A over 2 squared, which is the radius squared, times pi. And we can simplify this as A squared over 8 pi. We can repeat the same process for the area A2 for the semicircle on the left, only this time the radius will be B over 2, and we will get that the area is B squared over 8 pi, and finally the same thing for the area A3 for the semicircle on the bottom, and we will get the area C squared over 8 pi. Now let's try to find the sum of the areas A1 and A2. Again, we will substitute our values, and you can see that again we have the same denominator, so we can group this and get that that is quantity of A squared plus B squared over 8 pi. Now, again, A squared plus B squared equals to C squared, and you can see that again we have the value of the area A3. So in this way, we have proven that A1 plus A2 equals to A3 even in the case of the semicircles. So with this awesome knowledge in your mind, you can clearly and easily solve any type of problem which is similar to this one. And let's again try it on our problem. So remember, we got 2 semicircles which are erected from 2 sides of our right angle triangle, and we have this big semicircle in the middle, which is actually the semicircle which is erected from the hypotenuse of our right angle triangle. And as you can see, we have the same situation as the one which I explained to you a couple of seconds ago. So we clearly know that A1 plus A2 equals to A3. And now it's quite easy to solve our problem. We can also label the area of our right angle triangle, and from this we can say that our wanted area is equal to the sum of the areas A1, A2 and the area of the triangle, minus the area of the semicircle which is erected from the hypotenuse of our triangle, and we have labeled this one as A3. Now, since A1 plus A2 equals to A3, we can cancel those values, and we got that our wanted area is equal to the area of the right-angled triangle, and of course, we got that that value is equal to 6 squared units in this particular problem. So I really hope you guys enjoyed this problem, and I hope that you learned something new today. If you did, please do not hesitate to leave a like or subscribe to the channel for more content like this in the future. And of course, if you found another way to solve this problem, maybe even faster way, please write it down in the comment section below. And until next time, see you guys and take care.